The adjacency list structure maintains a mapping of vertex identifiers to their respective neighbor collections. Each vertex entry contains an unordered set of connected vertices, represented internally as a hash table with linear probing collision resolution. The iteration order over neighbors is not guaranteed to reflect insertion sequence. Access time for single neighbor lookup is a 1 average case, assuming uniform hash distribution across the identifier space. Graph construction begins with vertex registration through the adVertex method. This operation allocates a new entry in the primary index and reserves memory for the neighbor collection. The initial neighbor set has a default capacity of 16 entries, with automatic expansion occurring when load factor exceeds 0.75. Duplicate vertex registration returns a status code indicating the vertex already exists without modifying state. Edge insertion is performed via the addEdge method, which accepts source and destination vertex identifiers. The operation appends the destination identifier to the source vertex's neighbor set. If the source vertex does not exist in the adjacency list, the method returns error code 404 without creating intermediate entries. Bidirectional edges require two separate adEdge invocations for directed graph semantics. The getNeighbors method returns an iterator over the neighbor set for a specified vertex. The iterator provides sequential access to all connected vertices without guaranteeing order. Modification of the neighbor set during iteration is not permitted and will result in a concurrent modification exception. The iterator maintains an internal snapshot of the neighbor collection taken at instantiation time. Neighbor set capacity is managed through a dynamic resizing algorithm. When the number of stored neighbors exceeds 75% of current capacity, the set is rehashed with double the previous capacity. The rehashing process is performed in place with a temporary buffer. Memory overhead during rehashing is equivalent to the current neighbor set size. Rehashing does not modify the logical contents of the graph structure. Edge deletion is implemented through the removeEdge method, which removes a destination identifier from the source vertex's neighbor set. If the edge does not exist, no state modification occurs and a status code is returned indicating absence. The removal operation performs a linear scan through the neighbor set to locate the target identifier, resulting in OK time complexity where K is the number of neighbors. The containSEdge method performs a membership test on the neighbor set for a given vertex pair. This operation uses hash table lookup to determine edge existence in a 1 average time. The method returns a Boolean value without raising exceptions for non-existent vertices or edges. No state modification occurs during the containSEdge operation. Vertex degree computation via the getDegree method returns the cardinality of the neighbor set for a specified vertex. For directed graphs, this represents the outDegree. InDegree queries require separate iteration over all vertices. The getDegree operation executes in a 1 time by maintaining a size counter within each neighbor collection. Degree updates occur automatically during edge addition and removal. The neighbor set supports filtering through predicate-based iteration. The getNeighbors method accepts an optional filter function which is applied to each neighbor identifier. Filtered iteration does not skip hash table entries, but rather evaluates the predicate before yielding results. Filter functions must not modify the neighbor set during evaluation. Memory allocation for filtered results is deferred until iteration begins. Hash collision resolution within neighbor sets employs linear probing with step size of 1. When a collision occurs during insertion, the next available slot is examined sequentially. The maximum probe sequence length is bounded by capacity minus current size. Collision chains are not explicitly maintained. The load factor constraint prevents probe sequences from exceeding reasonable lengths in practice. Serialization of adjacency lists is performed through the export method, which writes vertex identifiers and their neighbor sets in a structured format. Each vertex entry is written with a header containing the vertex identifier and neighbor count, followed by sequential neighbor identifiers. The serialization order reflects the internal hash table iteration order. Deserialization reconstructs the graph structure without guaranteeing identical internal layout. The clearNeighbors method removes all edges for a specified vertex, while preserving the vertex itself in the adjacency list. This operation resets the neighbor set to an empty state and deallocates the hash table. The vertex entry remains registered with capacity reset to the default value. clearNeighbors does not affect other vertices or their neighbor relationships. The operation completes in 01 amortized time. Memory statistics for the adjacency list are accessible through the getMemoryUsage method. This returns the total bytes allocated for the primary vertex index and all neighbor sets combined. The reported usage includes hash table overhead and internal fragmentation from resizing operations. Statistics are calculated on demand without maintaining a separate counter. Large graphs may experience memory usage exceeding the theoretical minimum by 10 to 20%. Neighbor set iteration state is not persistent across method calls. Separate iterator objects must be maintained for continued access. Restarting iteration from a saved position requires manual tracking of the last accessed vertex. No built-in iterator state serialization is provided. Concurrent iteration over the same vertex's neighbors from multiple threads is not supported without external synchronization. The replace neighbor method removes a specified neighbor and inserts a replacement in a single atomic operation. This operation is semantically equivalent to performing remove edge followed by add edge, but without intermediate state exposure. The replacement neighbor must be a valid registered vertex. If the original neighbor does not exist, the method returns error code without creating the replacement edge. Vertex removal through the remove vertex method deletes the vertex entry from the primary index and deallocates its neighbor set. All incoming edges from other vertices must be removed separately as the adjacency list does not maintain reverse indices. The vertex identifier is not reclaimed for future registration. Removing a non-existent vertex returns a status code without raising exceptions. This operation completes in O(n) time where n is the total number of edges.